Welcome to a deep dive specifically tailored for you. Today we're tackling a paper from 2015 that fundamentally changed how we train deep neural networks.
It really did. Before this paper, training deep networks was, well, let's just say challenging. One of the biggest headaches was something called internal covariate shift.
Right. Okay, so imagine a deep network, lots of layers.
Yeah.
As you train it, tweaking the parameters in the early layers, the inputs to the later layers are constantly changing their statistical properties. Their mean, their variance, they're sort of shifting around.
And this paper actually defines internal covariate shift precisely as the change in the distribution of network activations due to the change in network parameters during training. It's quite specific.
Okay, so why is this shifting distribution such a big deal? I mean, what's the actual consequence for training?
Well, the main problem is that downstream layers constantly have to adapt to this moving target input distribution.
Right.
It's like trying to learn to catch a ball. But the person throwing it keeps changing how they throw with every single toss. It just significantly slows down the learning process.
Right, because the later layers never get a stable signal to learn from effectively.
Exactly. And this gets worse. The deeper the network is, amplifying the shift layer by layer.
Makes sense.
But here's where it gets particularly tricky, and the paper really highlights this. Consider using, say, a sigmoid activation function.
Or
If the inputs to a layer with a sigmoid get too far from zero, either, very positive or very negative.
the dreaded saturated regions.
Precisely. If internal covariate shift causes the distribution of inputs to a sigmoid layer to drift into these saturated areas, the gradients that backpropagate through that layer essentially vanish. Just poof, gone.
Right, the vanishing gradient problem.
Exactly. And this makes training incredibly slow, or it can just halt learning altogether for that layer and anything earlier in the network.
So before this paper, people were using various workarounds to try and avoid this, right? Like careful initialization of weights.
Using very small learning rates, or just sticking to non-saturating functions like ReLU, which don't quite have this problem in the same way.
Yes, those were definitely common strategies, but they were often, let's say, fragile or limiting. The paper proposed a more direct solution, batch normalization.
And that's our mission today. We're going to unpack this paper, really understand what internal covariate shift is, break down step-by-step how batch normalization works based on their description.
Yeah, get into the nitty-gritty.
And reveal the dramatic impact it had. I mean, achieving state-of-the-art results much, much faster than before is pretty impressive.
Okay, let's dive deeper into how batch normalization, or BN, addresses this internal covariate shift. The core idea is, well, to stabilize the distribution of layer inputs by normalizing them.
Normalization. Okay, so we've heard of normalizing inputs to a network overall, right? Like making the pixel values of images have zero mean and unit variance before you even feed them in. Exactly. And the paper points out that normalizing inputs to a network that's long been known to help with convergence. So the idea they explored was applying a similar concept within the network to the inputs of each layer. Now, a standard way to stabilize distributions is something called whitening.
Whitening?
Yeah, forcing them to have zero mean unit variance and, crucially, be decorrelated.
But applying full whitening within a deep network during training, that sounds complicated. And maybe expensive.
It is. The paper notes that calculating and inverting covariance matrices for full whitening is computationally heavy. But maybe more fundamentally, if you calculate these normalization statistics outside the gradient backpropagation step, they showed you can run into weird problems where parameters just grow indefinitely without actually changing the network's output because the normalization is constantly just undoing the effect of the parameter changes.
Oh, wow. Okay, so that's not good. They needed a way to normalize that was like simpler.
Simpler, yeah.
Differentiable, right. So it could be integrated seamlessly into training with gradient descent.
Right. And batch normalization introduces two key simplifications compared to that full whitening idea. The first is simplifying the whitening itself.
Okay.
Instead of whitening jointly across features to decorrelate them, which is complex, batch norm just normalizes each scalar feature independently. Yeah, just gives each feature a mean of 0 and unit variance on its own. The authors found that even this simplification without the decorrelation part still significantly speeds up convergence.
Okay, so simplifying the transformation itself makes sense. What's the second simplification?
This one is really crucial for using stochastic gradient descent, with mini batches. Instead of calculating the mean and variance over the entire training data set, which, as you can imagine, is impractical during mini batch training.
Totally impractical, yeah.
Batch normalization uses the mean and variance of the current mini batch as estimates.
Ah, okay, so the statistics actually change with every single mini batch.
Yes, they do. And this means the normalization process itself is dependent on the specific mini batch you're processing. And this dependency can actually be included in the gradient calculation during backpropagation.
Okay, let's walk through what happens for a single activation, like a single value in the input to a layer, as described in the paper, for a mini batch of these values.
Okay, so first you calculate the mean of all those values just within that mini batch. That's your mini batch mean. Simple enough.
Got it, the average in the batch.
Then you calculate the variance of those values, again, just across the mini batch. They add a tiny constant epsilon here just for numerical stability, in case the variance happens to be 0.
Right, avoid dividing by 0. Okay, mini batch variance.
Next, for each individual value in that mini batch, you normalize it. You subtract the mini batch mean you just calculated and divide by the square root of the mini batch variance, plus that little epsilon.
So now, within that specific mini batch, these normalized values have a mean of 0 and a variance of 1. They're standardized for that batch.
Correct. But, and this is a really important point the authors make, simply forcing everything to have 0 mean and unit variance might actually restrict the network's representational power.
How so?
Well, what if the network needs the activations to have a certain non-zero mean or maybe a different variance to represent the function it's trying to learn effectively? Like, forcing inputs to a sigmoid to always be around 0 might prevent it from learning transformations that actually rely on the saturated parts of the sigmoid.
Ah, that makes sense. You might be normalizing away potentially useful information about the distribution itself.
Exactly. So to counter this potential problem, the paper introduces 2 learnable parameters per activation. A scale parameter, they call it gamma, and a shift parameter, beta.
Okay, so learnable parameters. After you've normalized the value to have mean 0 and variance 1, what happens with gamma and beta?
You then scale the normalized value by shift it by beta, so the final output value from the batch normalization transform is actually y gamma hat plus beta.
Okay, scale and shift. And these gamma and beta parameters, they're not fixed.
No, that's the key. They are learned during training right alongside the network's weights and biases. This means the network can essentially learn to undo the normalization if that's what helps it learn better. If the optimal distribution for a layer's inputs is, say, the original pre-normalization distribution, the network can learn equal to the original standard deviation and beta equal to the original mean, effectively restoring the original distribution.
Wow. Okay, so it preserves the network's representational power. It doesn't force normalization if it's not helpful.
Exactly. It gives the network the flexibility.
Yeah.
And this whole process, calculating batch stats, normalizing, scaling, and shifting, is implemented as a fully differentiable transform. You just insert it into the network like any other layer, and gradient descent works as expected.
Okay, cool. So we've seen how it works during training, using those mini-batch statistics. But what happens when you've finished training and you just want to use the network to make a prediction on, say, a single new example? You don't have a mini-batch anymore.
Right. That's a really important distinction. During inference, you definitely want the network's output to be deterministic.
Yeah, same input, same output every time.
Exactly. You don't want the output for one image depending on what other images might happen to be processed alongside it. Relying on mini-batch statistics during inference would introduce that kind of unwanted variability.
So you can't use those mini-batch means and variances for inference. What do you do instead?
Correct. The paper explains that during training, in addition to calculating the mini-batch statistics for the normalization and gradients, the network also keeps track of running averages. Think of them like moving averages of the mini-batch means and variances it sees over time.
Okay, so it's building up an estimate of the overall statistics.
Precisely. This running average provides a stable estimate of the population mean and variance for each activation, averaged over the entire training data set, essentially.
Got it. An estimate of the mean and variance the activation would have on average over all possible training data it might see.
Exactly. Then, during inference, when you feed in that single example, instead of calculating mini-batch stats, the batch normalization layer uses these learned fixed population means and variances for the normalization step.
Ah, okay, so fixed values based on the training history.
Right. And the learned gamma and beta parameters are still applied after that normalization, just like during training.
And the paper notes that during inference, this can actually be made very efficient, right?
Yes, absolutely. Once you have the fixed population mean, the fixed population variance, and the learned beta for an activation, the whole operation for a single input normalizing, using the fixed stats, scaling by shifting by beta, can all be mathematically combined and pre-computed into just a single linear transformation, a multiply and an add. So inference is really fast.
Okay, that's clever. So where exactly do you typically stick this batch normalization layer within a network architecture?
Good question. The authors generally recommend placing it right before the nonlinearity of a layer.
Before the activation function like ReLU or sigmoid.
Exactly. So if a layer normally does a linear transformation, say wu plus b, and then applies a nonlinearity g.
You'd have ZG wu plus B.
Right. With batch norm, it becomes zbn wu plus b, or actually even more commonly, you'll see zbn wu.
Without the bias term, the B.
Yeah, because think about it. The bias b in wu plus b is just adding a constant shift. But the batch norm step itself involves subtracting the mean.
So the mean subtraction would cancel out the bias anyway.
Pretty much, yeah. Its role is effectively taken over by the learned shift parameter beta in the batch norm layer. So often you just drop the original bias term when you're using batch norm right after the linear transformation. Woo.
Okay, that simplifies things. But why specifically before the nonlinearity?
Well, the paper suggests that the output of the linear transformation, the woo, is more likely to have a distribution that's, let's say, more Gaussian or at least less sparse than the input might be.
Especially if it's already the output of a previous nonlinearity like ReLU.
Exactly. ReLU introduces sparsity by setting negative values to 0. So normalizing the woo before it hits the next nonlinearity is thought to be more effective at stabilizing the distributions and ensuring the values are in a good range for that nonlinearity.
Keeping them out of those nasty saturate zones we talked about.
Right. It keeps the signal flowing nicely.
Okay, that makes sense. Now, how about convolutional networks? They have that spatial structure, the feature maps. How does BN work there?
Yeah, batch normalization adapts very naturally to convolutional layers. The key goal is to maintain the convolutional property. The idea that the same transformation, the same filter, is applied consistently across different spatial locations in a feature map.
Right, you don't want the normalization to depend on where in the image a feature appears.
Precisely. So to achieve this, the normalization statistics, the mean and variance for a given feature map, are calculated jointly. They're calculated over all the activations in that feature map,
Okay.
across the entire mini-batch and across all the spatial locations, the height and width, within those feature maps in the batch.
Whoa, okay, so for a single filter's output, a single channel or feature map, you calculate one mean and one variance using all the values produced by that filter across the whole batch and all the spatial locations.
Exactly that. You pool all those values together for the statistics. And crucially, you learn one pair of gamma and parameters per feature map.
Just one gamma and beta for the whole channel, not one for each pixel location.
Right. This ensures that the normalization, scaling, and shifting are consistent for that feature map, regardless of where the activation occurs spatially. It respects the convolutional structure.
Got it. Now, batch normalization was primarily designed, as we said, to fix internal covariate shift and the training headaches that came with it. But the paper found it had some really significant positive side effects too, right? Beyond just stabilization.
It absolutely did. It brought some, frankly, amazing and somewhat unexpected benefits that further accelerated training and often improved performance. One of the biggest ones was the ability to use much, much higher learning rates.
Wow, okay, that's huge. Higher learning rates usually mean faster training, but they also carry the risk of instability or the whole thing just blowing up.
Yeah.
Why did batch norm make higher learning rates possible?
Well, the authors explain it a couple of ways. By stabilizing the distributions and preventing inputs from constantly being pushed into saturated regions where gradients die. Batch norm basically prevents small changes in parameters from being drastically amplified into huge changes in activations or gradients down the line. It keeps the gradients much more well-behaved.
So it smooths out the optimization landscape, in a sense.
Yeah, that's a good way to put it. They also noted that backpropagation through a BN layer is less affected by the overall scale of the layer's weights. Even if the weights themselves grow large, the resulting activations get normalized anyway, which helps prevent gradients from exploding.
That's a really powerful stability mechanism.
Mm.
You also mentioned earlier it had a regularizing effect. That seems counterintuitive almost.
Yeah, this was definitely a surprising finding for them too. Remember, the normalization statistics for each training example depend on the other examples in its current mini-batch.
Right, because it uses the mini-batch mean invariance.
So the network sees a slightly different normalized version of the same input example depending on which specific batch it happens to fall into. This introduces a tiny amount of noise or randomness into the training process for each example.
And that noise acts as a regularizer.
Exactly. Similar in effect to something like dropout, where you randomly zero out activations.
Huh. And in their experiments, they actually found they could reduce or even completely eliminate the need for dropout.
Yes, and also use weaker L2 weight regularization. And interestingly, doing so often improved the final validation accuracy, suggesting BN's regularization was perhaps more effective or complementary.
That's fascinating. Okay, what else?
Well, another major benefit we touched on earlier, but it's worth stressing, by consistently keeping inputs out of those saturated zones.
Yeah.
Batch normalization made it practical again to train deep networks effectively using saturating nonlinearities like sigmoids or hyperbolic tangents, which had been notoriously difficult, almost impossible, for very deep networks before.
So it opened up architectural options that had been effectively closed off.
Right. And finally, sort of related to the stability aspect, the paper notes that batch norm makes the network training much less sensitive to the initial values of the parameters.
Oh, that's another huge headache relief for practitioners. Parameter initialization can be a real dark art.
It really removed, or at least lessened, a lot of common tuning pain points, made life easier.
The real proof of the pudding, though, as they say, is in the results they showed in the paper.
Absolutely, and they backed it up thoroughly. They started with some simple experiments, like on MNUST, basically showing visually how adding batch norm dramatically stabilizes the distribution of inputs to sigmoid layers over time.
Like, you could actually see the distribution staying centered.
Yeah, compared to the baseline network where the distributions just drifted all over the place, if you look at figure 1 in the paper, it's really clear. You can see that stabilization happening.
Okay, but the really compelling evidence came from applying batch norm to a then state-of-the-art image classification network on the big, challenging ImageNet dataset. They used a variant of the inception model, right?
That's right. They ran several key comparisons. First, the original inception network served as the baseline. Then they had a version called BN baseline.
Which was just adding batch norm.
Yep. Simply added a batch normalization before each nonlinearity in the existing inception network architecture. No other changes.
Okay. And then they had the networks that really showed the potential, the accelerated BN networks. I think they called them BN by 5 and BN by 30.
Correct. And these didn't just have batch norm. They fully embraced the possibilities BN opened up. They incorporated training modifications, like significantly increasing the learning rate 5 times or even 30 times higher.
Oh.
Plus, removing dropout entirely, reducing L2 regularization, using a faster learning rate decay schedule, and even more aggressive data shuffling during training. Really pushing the envelope because BN allowed it.
Okay, so what happened? How did they perform?
The results were just incredibly striking. You can see it clearly in figures 2 and 3 from the paper. Just adding batch norm alone, the BN baseline version, allowed the network to match the accuracy of the original inception model in less than half the training steps.
Less than half. So immediately over twice as fast, just by adding BN layers.
Yeah, something like 13.3 million steps versus 31 million steps for the original to reach the same accuracy mark.
Wow. Okay, impressive already. But the accelerated versions, BN by 5.
That's where it gets really dramatic. The BN by 5 network, the one with batch norm and the 5x higher learning rate and other tweaks, it reached that same accuracy level 14 times faster than the original inception network.
14 times. Seriously.
Seriously, it took only about 2.1 million steps compared to the original's 31 million steps. Just an incredible speed up.
That is absolutely incredible. 14 times faster just by adding batch norm and cranking up the training settings it enabled. What about BN by 30 with the even higher 30x learning rate?
So BN by 30, using that super high learning rate, actually trained a little bit slower right at the very beginning compared to BN by 5. But interestingly, it ultimately reached a higher final accuracy.
Higher than the original inception.
Higher than both the original and BN by 5. It got to 74.8% top one accuracy compared to about 72.2% for the original inception.
Okay, so not only faster, but better performance in the end. And how fast did it get to that higher accuracy?
Even achieving that higher accuracy, it still got there much, much faster than the original network took to reach its lower accuracy. BN by 30 reached its peak in about 6 million steps, compared to the original's 31 million steps to reach its lower peak.
That's just undeniable proof of both massive speed up and improved final performance.
Amazing. And did they show that sigmoid thing work too on ImageNet?
They did. They tested a BN by 5 network, specifically using sigmoid nonlinearities instead of the usual ReLUs. It achieved a respectable accuracy, around 69.8%. Now, critically, they also mentioned that the original Inception network architecture, if you just swapped ReLUs for sigmoids without batch norm, completely failed to train. It just stayed stuck at chance accuracy.
Wow, so that experiment really nailed the point that batch norm makes these saturating functions usable again, even in very deep networks on complex tasks.
Exactly. Clear validation.
And finally, I think they pushed for the absolute best possible result by combining multiple networks, right? An ensemble. Right, that's in figure 4. By taking an ensemble, combining predictions from several networks trained with the BN by 30 recipe plus some minor variations,
Yeah.
they achieved a new state-of-the-art result on the ImageNet benchmark at the time. Their top 5 error rate dropped to 4.9% on the validation set and 4.82% on the test set.
And wasn't there a comment about human performance?
Yes. The authors proudly pointed out in the paper that this level of error, 4.82%, actually exceeded the estimated accuracy of human raters performing the same image classification task at that time.
So batch normalization didn't just speed things up. It helped push machine performance beyond human levels on this benchmark. Incredible.
Truly a landmark result.
So just to recap the sheer power of batch normalization here, by tackling this problem of internal covariate shift, this constantly changing distribution of inputs inside deep layers, through a, let's face it, surprisingly simple and differentiable normalization process using mini-batch statistics.
Elegant in its simplicity, really.
This paper didn't just fix a nagging problem. It fundamentally revolutionized deep network training.
It really did. It led to these massive speed-ups we saw, often better final performance. It allowed practitioners to confidently use much higher learning rates. It provided this useful regularization effect that often let them ditch dropout.
Yeah.
And it made previously difficult or impossible choices, like using sigmoid nonlinearities in deep nets, viable again. It just dramatically simplified and accelerated the whole deep learning workflow.
The paper concluded, I believe, by suggesting some potential future work.
Yeah, they pointed towards areas like applying batch norm ideas to recurrent neural networks, RNNs, where vanishing and exploding gradients are also a really major challenge. They also mentioned exploring its use in domain adaptation scenarios and called for more theoretical analysis to fully understand why it provided all these diverse benefits.
It's definitely a paper that left, as you said, an indelible mark on the field. It's hard to imagine modern deep learning without it or its descendants.
Absolutely standard practice now.
And it leaves us with perhaps a final provocative thought for you, our listener, to consider. The authors of this paper showed how stabilizing the internal distributions of activation values, something happening deep inside the network, could unlock such tremendous improvements in overall training speed and final performance. So the question is, what other seemingly subtle adjustments to the flow or the properties of information inside these incredibly complex learning systems could be waiting out there to dramatically change the game next?